In this lesson, we're going to take a look at freefall, and freefall just means that an object is got only one force acting on it, and that's the force due to gravity. And when that's true, it's got one acceleration, and that's the acceleration due to gravity. So freefall, only gravity acts. Now, we're not quite into dynamics yet, so we're not really going to talk about the forces or what gravity is. We just know that if the only influence acting on an object is gravity, then it will accelerate towards Earth at a constant, with a constant acceleration, and that acceleration is g, and g is 9.8 meters per second per second. So if something is in free fall, so the only force acting on it is gravity, then it'll accelerate towards Earth at 9.8 meters per second per second. Now if we're not on Earth, that number changes, but we still call it g. Little g is the acceleration due to gravity. And so we have this misconception sometimes that an object has to be moving down or towards Earth to be in free fall, but that's not the case. If I throw something straight up and I let go of it, then the only thing acting on it after I let go is gravity, and it's in free fall. Now there is the idea of air resistance, and we're not going to deal with air resistance, at least not until later. So we're going to consider an object that is falling to be in free fall, or an object that's going straight up to be in free fall. We're not going to consider air resistance. Now if we think about an object that we throw straight up in the air, it goes up and it comes back down. But let's think about how it changes with time. And then we're going to jump into a graph for a minute. And so I'm going to think about its velocity graph. Okay? And I'm going to need some negative on this. So here's 0 meters per second. This is velocity. Here's time. Now, when I throw it, when it comes out of my hand, when the problem starts, it's going to have a fairly high positive velocity, assuming that I threw it up, and up is the positive direction. So it starts like this. Now, as it continues to move up, it gets slower and slower and slower and slower and slower and slower until it reaches its highest point. Now, at its highest point, it stops for just a split second, an instant in time, and then it reverses direction and it continues to accelerate down towards Earth, this time getting faster, right? So this line shows a reverse in direction, but it's got a constant slope because it's got a constant acceleration. The entire time this object is accelerating towards Earth. And so at the beginning, the velocity is up, but the acceleration is down, and because of that, it gets slower. But at the end, the velocity is down and the acceleration is down, and because of that, the speed gets higher. The velocity becomes more negative, right? And so that shows an object in free fall on its velocity time graph. On a position versus time graph, that would look like this, right? Starts close, gets fast, gets slow, turns around, gets faster, right? It's a parabola. It's an inverted parabola. And we, in fact, can come up with the equation that describes that motion. So this is free fall. The slope of this is g, and g equals 9.8 meters per second per second. And because we chose our reference point to show up as positive, this would be negative 9.8 meters per second per second. On the position time graph, remember the equation that we have is x equals 1/2 at squared plus v naught t plus x naught. Well, this is written for horizontal motion, and we consider x to be horizontal position. But all I have to do to go to vertical is go y equals 1/2 at squared plus v naught t plus y naught, right? And so now I've got heights instead of positions, so it's just height measured up and down instead of left and right. Now, the acceleration is the acceleration due to gravity. So if a equals g, this becomes y equals 1/2 negative 9.8 t squared plus v naught t plus y naught. Now, 1/2 of negative 9.8 is negative 4.9. So we have y equals negative 4.9 t squared plus v naught t plus y naught. Okay, that's cool because the coefficient on the time squared term tells us half the acceleration. And so if we have a position time graph, we can just look at the equation of that curve and know what our acceleration is. Now, if we're solving free fall problems, is just like solving any other problem with the kinematic equations. We just know that our acceleration is negative 9.8 meters per second, assuming we picked up to be a positive direction. And so this parabola actually has this cool spot up here, which corresponds to this right there, right? That's its highest point. That's when its velocity is 0. So one common mistake that people make when they're solving free fall problems is they say that it's got an initial velocity of 0 or a final velocity of 0, and that's not the case. What we can say is the velocity is 0 at the highest point. Okay. Now sometimes that corresponds to the initial spot, right? If I drop something, then its highest point is when I let go and it's got an initial velocity of 0. Sometimes it's right in the middle, right? If I throw something up and it comes back down and it falls and lands at the same height it started, then symmetry tells us that this has to be in the center or the middle of time, right? So it took just as much time to go up as it took to come back down. But if we throw something or drop something off of a cliff or throw something up off of a cliff and let it come like this, then the time it takes to get back to its original position, these two intervals would match, but then it's got all that time that it takes to fall back down. So that doesn't necessarily match. So if it starts and ends at the same height, then we can say it's at its highest point in the middle of the motion. But if it does not start and end at the same height, then we'd have to say, well, we know it's got a final velocity of 0 when its highest point is 0, which may or may not be halfway through its time interval.